Hello, my dear, and welcome to our astronomy course. Today we have lecture number 17, and we in this lecture we will be continuing study the galaxy. Okay? So let's start. Rotation curves reveal the motion of the outer part of a galaxy. But it is also possible to detect the Doppler shift of stars. I hope you remember about Doppler shift. Yes? Doppler shift of stars orbiting close to the galaxy center. Also, these motions are not usually shown on rotation curves. They reveal something astonishing. Measurements show that the stars near the centers of most galaxies are orbiting very rapidly. To hold stars in such small and short period orbits, the centers of galaxies must contain masses of 1 million to a few billion solar mass. Imagine this mass, this value. Yet no objects are visible, suggesting that the nuclei of galaxies contain supermassive black holes. You saw in the previous lecture that the Milky Way contains a supermassive black hole in its center. Evidently, that is typical of galaxies. Such a supermassive black hole cannot be the remains of the dead star. That would produce a black hole of only a few solar masses. A few dozen central black holes have measured masses, and those supermassive black holes typically contain only 0.5% the mass of the nuclear bulge. A galaxy with a large nuclear bulge has a supermassive black hole whose mass is greater than the supermassive black hole in a galaxy with a small nuclear bulge. And this implies that the supermassive black holes formed long ago as the galaxies began forming. Of course, matter has contained to the drain into them, but they do not appear to have grown dramatically since they formed. A billion solar mass black hole sounds like it contains a lot of mass, but no, that it is only about 1% of the mass of a galaxy. The 3.7 million solar mass black hole at the center of the Milky Way galaxy contains only 0.1% of the mass of the galaxy. In the next module, you will discover that these supermassive black holes can produce titanic eruptions. Given the size and luminosity of a galaxy, astronomers can make a rough guess as to the amount of matter it should contain. Astronomers know how much light stars produce, and they know about how much matter there is between the stars. So it is quite possible to estimate very roughly the mass of a galaxy from its luminosity. But when astronomers measure the masses of galaxies, they find that the measured masses are much larger than expected given their luminosity. In the previous lecture, you studied the rotation curves of our own galaxy and concluded that it must contain large amounts of dark matter. This seems to be true of most galaxies. Measured masses of galaxies detect about 10 times more mass than you would expect given the brightness of the galaxy. X-ray observations reveal more evidence of dark matter. X-ray images of galaxy clusters show that many of them are filled with very hot and low-density gas. The amount of gas present is much too small to account for the dark matter. And rather, the gas is important because it is very hot and its rapidly moving atoms have not leaked away. Evidently, the gas is held in the cluster by a very strong gravitational field. To have enough gravity to hold such hot gas, the cluster must contain much more matter than it is visible. The detectable galaxies in the Coma cluster, for instance, amount to only a small fraction of the total mass of the cluster. Let's look to this figure, please. When you solve a math problem and get an answer that doesn't seem right, you check your work for a mistake. It's typical for all scientists do the same. Astronomers using the rotation curve method and the cluster method to measure the masses of galaxies have found evidence of large amounts of dark matter. So they look for ways to check their work. Fortunately, there is another way to detect dark matter that doesn't depend on observing orbital motion. You can understand how it works by following a light beam. Albert Einstein described gravity as a curvature of space-time. The presence of mass actually distorts space-time around it, and that is what you feel as gravity. Einstein predicted that a light beam traveling through a gravitational field would be deflected by the curvature of space-time, much as golf ball is deflected as it rolls over a curved putting green. That effect has been observed and is a strong confirmation of Einstein's theory. Gravitational lensing occurs when light from a distant object passes a nearby massive object and is deflected by the gravitational field. The gravitational field of the nearby object is actually a region of curved space-time that acts as a lens to deflect the passing light. Astronomers have used gravitational lensing to detect dark matter. When light from very distant galaxies passes through a cluster of galaxies on its way to Earth, it can be deflected by the strong curvature that distorts the images of the distant galaxies into arcs. And the amount of the distortion depends on the mass of a cluster of galaxies. Let's look to this figure, please. Observations of gravitational lensing made with very large telescopes confirm that clusters of galaxies contain far more matter than when it seems. And that is, they contain large amount of dark matter. And this confirmation of the existence of dark matter is independent of orbital motion and gives astronomers much greater confidence that dark matter is real. Dark matter is difficult to detect, and it is even harder to explain. Some astronomers have suggested that dark matter consists of a low luminosity white dwarf and brown dwarfs scattered through the colors of galaxies. Both observation and theory support the idea that galaxies have massive extended halos, and searches for white dwarfs and even brown dwarfs in the halo of our galaxy have been successful. Nevertheless, the searchers have not tuned up enough of these low luminosity objects to make up all the dark matter. Recall from the previous module, the dark matter can't be hidden in vast numbers of black holes and neutron stars because astronomers don't see the X-rays these objects would emit. There is roughly 10 times more dark matter than visible matter, and that many black holes would produce enough X-rays to be easily detected. Okay? Because observations imply that the dark matter can't be hidden in the normal object. Theorists suspect that the dark matter is made up of an unknown form of planet. Sorry, not a planet, a known form of matter. Until recently, neutrinos were thought to be massless, but newer studies now suggest that they have a very small mass, and thus they could be part of the dark matter. But their masses are much too low to make up all of it. There must be some other undiscovered form of matter in the universe that is detectable only by its gravitational field. Dark matter is not a small issue. Observations show that nearly 85% of the matter in the universe is dark, namely dark matter. The universe you see, the kind of matter that you and the stars are made of, has been compared to the form on an invisible ocean. Dark matter remains one of the fundamental unresolved problems of modern astronomy. You will return to this problem in a later module when you try to understand how dark matter affects the nature of the universe, its past, and its future too. Your goal in this module is to build a theory to explain the evolution of galaxies. In the previous lecture, you developed a theory that described the origin of our Milky Way galaxy. Presumably, other galaxies form similarly. But why did some galaxies become spiral, some elliptical, and some irregular? Clues to that mystery lie in the clustering of galaxies. The distribution of galaxies is not entirely random. Galaxies tend to occur in clusters containing anywhere from a few galaxies to thousands. Deep photographs made with the largest telescope reveal clusters of galaxies scattered out to the limits of detectability. For this discussion, you can sort clusters of galaxies into two groups, rich and poor. Rich galaxies clusters contain over 1,000 galaxies, mostly elliptical, catered through a spherical volume about 3 megaparsecs, or it contains 107 light years in diameter. Such a cluster is very crowded, with the galaxies more concentrated towards the center. Rich clusters often contain one or more giant elliptical galaxies at their center. The Coma cluster, located in the constellation Coma Berenices, is an example of a rich cluster. Let's look at this slide, please. It lies over 100 megaparsecs from Earth and contains at least 1,000 galaxies, mostly E and S not galaxies, according to the classification. Its galaxies are highly crowded around the central giant elliptical galaxy and the large S not. Where galaxy clusters contain fewer than thousands galaxies, they're irregularly shaped and are less crowded. Our own local group, which contains the Milky Way galaxy, is a good example of a Fourier cluster, as you can see in this slide. It contains a few dozen members scattered irregularly through a volume slightly over 1 megaparsec in diameter. Of the brightest galaxies, 14 are elliptical, 3 are spiral, and 4 are irregular. The total number of galaxies in the local group is uncertain because some lie in the plane of the Milky Way galaxy and are difficult to detect. For example, a small dwarf galaxy known as a Sagittarius dwarf has been found on the far side of our own galaxy, where it is almost totally hidden behind the star clouds of Sagittarius. You may see this on figure B in this part of the town of this slide. Even closer to the center of the Milky Way galaxy is the Canis Major dwarf galaxy, as you may see on opposite part of this slide on the figure C. The galaxy was found by mapping the distribution of red supergiants detected by the 2-mass infrared survey. Other small galaxies in our local group have been found hidden behind the stars, gas, and dust of our Milky Way galaxy. Classifying galaxy clusters into rich and poor clusters reveals a fascinating and suggestive clue to the evolution of galaxies. You know, in general, rich clusters tend to contain 80 to 90% E and S naught galaxies and a few spirals. Poor cluster contains a larger percentage of spirals. Among isolated galaxies, those are not in clusters. 80 to 90% are spirals. And this suggests that a galaxy's environment is important in determining its structure and has led astronomers to suspect that the secrets to galaxy evolution lie in collisions between galaxies. You should not be surprised that galaxies collide with each other. The average separation between galaxies is only about 20 times their diameter, like two blindfolded elephants blundering about under a thick stand. Galaxies should bump into each other once in a while. Stars on the other hand, almost never collide. In the region of our galaxy near the Sun, the average separation between stars is about 107 times their diameter. A collision between two stars is about, not 100, 10 in power 7. So imagine that big number, 7 zeros, yes, their diameter. Study interacting galaxies and notice 4 important points and 3 new terms here. And first of all, is interacting galaxies can distort each other with time, producing tidal tails and shells of stars. Encounters between galaxies may trigger the formation of spiral arms. Large galaxies can even absorb smaller galaxies, a process called galactic cannibalism. Interaction between galaxies can trigger star formation. And evidence left inside in the form of motion and multiple nuclei reveals that they have suffered past interactions and mergers. And finally, the beautiful ring galaxies are bull's-eye left behind by high-speed collisions. Evidence of galaxy merging is all around you. Our Milky Way galaxy is a cannibal galaxy snacking on the Magellanic Clouds as they orbit past. Its tides are pulling the Sagittarius dwarf galaxy apart, and the Canis Major dwarf galaxy has been almost completely digested as tides pull stars away to form great streamers wrapped around the Milky Way galaxy. Almost certainly, our galaxy has dined on the other small galaxy. The nearby Andromeda galaxy appears to be doing the same thing. Its halo contains streams of stars and star clusters that it has stripped from its form of small nearby galaxies. The test of any scientific understanding is whether you can put all the evidence and theory together to tell the history of the object study. Can you describe the origin and evolution of the galaxy? Just a few decades ago, it would have been impossible. But the evidence from space telescopes and new generation telescopes on Earth, combined with advances in computer modeling and theory, allows astronomers to outline the story of the galaxy. As you begin, you should eliminate a few older ideas immediately. It is easy to imagine that galaxies evolve from one type to another. But an elliptical galaxy cannot become a spiral galaxy or an irregular galaxy, because elliptical contains almost no gas and dust from which to make new stars. Elliptical galaxies can't be young. You can also argue that a single spiral or a single irregular galaxy cannot evolve into an elliptical galaxy, because spiral and irregular galaxies contain both young and old stars. The old stars mean that spiral and irregular galaxies can be young. The galaxy classes tell you something important, but a single galaxy does not change from one class to another anymore. That a cat can change into a dog. Impossible, right? Another old idea was that each galaxy formed from a single cloud of gas that contracted and formed stars. Astronomers call such a proposal a top-down theory. The evidence is quite clear that a galaxy does not form by top-down contraction, but rather by a bottom-up accumulation of smaller clouds of gas and stars. Their inflow of gas and the absorption of small galaxies. The elliptical appear to the products of galaxy merges that triggered some formation and used up the gas and dust. In fact, astronomers see the star formation being stimulated to high levels in many galaxies. Star-burst galaxies are very luminous in the infrared because of collision has triggered a burst of star formation that hit the dust. The boom dust radiates the energy in the infrared. The antenna contains over 15 billion solar masses of hydrogen gas and will become a star-burst galaxy as the merger triggers rapid star formation. Supernova in a star-burst galaxy may eventually blow away much of the remaining gas and dust that doesn't get used up making stars. A galaxy that merges with a galaxy of similar size could be left with no gas and dust from which to make new stars. Astronomers now suspect that most ellipticals are formed by merger of at least 2 or 3 galaxies. Galaxies crowded in rich clusters collide often, and that explains why elliptical and S-naught galaxies are more common in such clusters. In contrast, spiral seems never to have suffered major collisions. They are thin disks and are delicate, and would be destroyed by the tidal forces during a collision with a similar sized galaxy. Also, they retain plenty of gas and tar and continue making stars. Galaxies in four clusters or isolated galaxies, not in any cluster, are unlikely to have collided with similar sized galaxies, so they remain spiral. Okay? Our own Milky Way galaxy has evidently never merged with another large galaxy, but it has clearly cannibalized smaller galaxies. Astronomers have found streams of stars in the core of our galaxy that are too metal-rich for their location. Another stream contains globular clusters with similar ages. These streams are evidently the remains of smaller galaxies that were absorbed. Parent spiral galaxies may be product of tidal interaction in which galaxies passes near each other but do not merge. Mathematical models show that parts are not stable and eventually dissipate. It may require tidal interaction with the other galaxies to regenerate the parts. because about two-thirds of all spiral galaxies have bars, and you can suspect that these tidal interactions are common. Other processes can alter galaxies. The S-node galaxies may have lost much of their gas and dust in a bars of star formation, but still manage to remain disk-shaped. Also, galaxies moving through the gas trap in the dense galaxy cluster and may have their own gas and dust blown away. For example, X-ray observations show that the Coma cluster contains thin, hot gas between the galaxies, as you may see in this slide. A galaxy moving through that gas would encounter a tremendous wind that would blow its gas and dust away. The dwarf ellipticals are too small to be made of merged spirals. Some dwarf ellipticals may have formed from small clouds of gas that were never incorporated in a larger galaxy. But other dwarf ellipticals, along with the irregular galaxies, may be small, scrambled fragments ripped from the larger galaxies during collision. A good theory helps you understand how nature works, and astronomers are just beginning to understand the exciting and complex story of the galaxy. Nevertheless, it is already clear that galaxy evolution is much like a pie-throwing contest and just about as neat. Observation with the largest and most sophisticated telescope are taking astronomers back to the age of galaxy formation. At great distances, the look-back time is so large, but they see the universe as it was soon after the galaxies began to form. One way to search for distant galaxies is to use gravitational lensing. When light from the very distant galaxy passes through a nearby cluster of galaxies, the lensing effect can focus the light from the distant galaxy, concentrate it, and make the galaxy look brighter. Using this technique, astronomers have found new galaxies that are so far away they have enormous look-back times, and we see them as they were roughly 500 million years after the universe began. These galaxies are small and blue with active star formation. They appear to be the first cloud of gas and stars that merged to begin forming galaxies. In the deep fields recorded by the Hubble Space Telescope, astronomers see faint red galaxies, as you may see in this slide. They look red because of their great redshift. The floods of ultraviolet light emitted by these star-forming galaxies have been shifted into the far red part of the spectrum. Okay? Their look-back times are so great that they appear as they were when the universe was only 900 million years old. These galaxies are smaller, bluer, and of lower luminosity than galaxies later in the history of the universe. At slightly smaller redshifts, astronomers see galaxies slightly later in the history of the universe and find that there were more spiral and fewer ellipticals than there are now. On the whole, galaxies long ago were more compact and more irregular. The observations show that galaxies were closer together than about 33% of all distant galaxies are in close pair, but only 7% of nearby galaxies are in pairs. This observational evidence clearly supports the bottom-up hypothesis that galaxies have evolved by merger. Now, let's start some scientific arguments. Why can't spiral galaxies be produced by merger? This argument draws on both theory and observation. Observations show that spiral galaxies have thin disks in which the stars move in regular, concentric orbits. Computer models show that mergers with similar-sized galaxies produce strong tides and destroy the disks and scramble the orbits of the stars. Such a merger could produce an elliptical galaxy with its random orbit, but it could not preserve the thin disk of a spiral galaxy. Now, revise your argument. What happens to the gas and dust in galaxies when they merge to form an elliptical galaxy? Let's summarize our lecture. Astronomers divide galaxies into three classes: elliptical, spiral, and irregular, with subclasses specifying the galaxy's shape. Elliptical galaxies contain little gas and dust and cannot make new stars. Consequently, they lack hot blue stars and have a reddish tint. Spiral galaxies contain more gas and dust in their disks and support active star formation, especially along the spiral arc. Some of the newborn stars are massive, hot, and blue, and that gives the spiral arm a blue tint. About two-thirds of spirals are barred spiral cars. The halo and nuclear bulge of a spiral galaxy usually lack gas and dust and contain little star formation. The halos and nuclear bulges have a reddish tint because they lack hot blue stars. Irregular galaxies have no obvious shape but contain gas and dust and support star formation. Galaxies are so distant astronomers measure their distances in megaparsecs, billions of parsecs. Astronomers find the distance to galaxies using distance indicators, sometimes called standard candles, objects of known luminosity. The most accurate distance indicators are the Cepheid variable stars. Globular clusters and type 1a supernova explosions have also been calibrated as distance indicators. By calibrating additional distance indicators using galaxies of known distance, astronomers have built a distance scale. The Cepheid variable stars are the most dependent. When astronomers look at a distant galaxy, they see it as it was when it emitted the light now reaching Earth. The look-back time to distant galaxies can be a significant fraction of the age of the universe. According to the Hubble law, the apparent velocity of a recession of a galaxy equals its distance times the Hubble constant. Look at this very simple expression. Astronomers can estimate the distance to a galaxy by observing its redshift, calculating its apparent velocity over a session, and then dividing by the Hubble constant. Once the distance to a galaxy is known, its diameter can be found from the small angle formula and its luminosity from the magnitude-distance relation. Astronomers measure the masses of galaxies in two basic ways. The rotation curve of a galaxy shows the orbital motion of its star, and astronomers can use the rotation curve method to find the galaxy's mass. The cluster method uses the velocities of the galaxies in a cluster to find the total mass of the cluster. The velocity dispersion method uses the velocities of the stars in a galaxy to find the total mass of the galaxy. Galaxies come in a wide range of sizes and mass. Some dwarf elliptical and dwarf irregular galaxies are only a few percent of the size and luminosity of our galaxy. But some giant elliptical galaxies are 5 times larger than the Milky Way galaxy. Stars near the centers of galaxies are following small orbits at high velocities, which suggest the presence of supermassive black holes in the center of the most galaxies. The mass of galaxy's supermassive black hole is proportional to the mass of its nuclear bulge. That shows that the supermassive black hole must have formed when the galaxy formed. Observations of individual galaxies show that galaxies contain roughly 10 times more dark matter than visible matter. The hot gas held inside some cluster of galaxies, and the gravitational lensing caused by the masses of galaxy clusters reveal that the clusters must be much more massive than can be accounted for by the visible matter. Further evidence of dark matter. Rich clusters of galaxies contain thousands of galaxies with fewer spirals and more elliptical. Our Milky Way galaxy is located in a poor cluster of galaxies called the local group. Poor clusters contains only a few galaxies with a larger proportion of spirals. This is evidence that galaxies evolve by collision and merging. When galaxies collide, tides twist and distort their shapes and can produce tidal tails. Large galaxies can absorb smaller galaxies in what is called galactic cannibalism. You can see clear evidence that our own Milky Way galaxy is devouring some of the small galaxies that orbit nearby, and that our galaxy has consumed other small galaxies in the past. Shells of stars, counter-rotating parts of galaxies, streams of stars in the hollows of galaxies, and multiple nuclei are evidence that galaxies can merge. Ring galaxies are produced by high-speed collision in which a small galaxy plunges through a larger galaxy perpendicular to its disk. The compression of gas cloud can trigger bursts of star formation, producing starburst galaxies. The rapid star formation can produce lots of dust, which is warmed by the star to emit infrared radiation, making the galaxy bright in the infrared. The merger of two larger galaxies can scramble star orbits and drive bursts of star formation to use up gas and dust. Large ellipticals have evidently been produced by past mergers. Spiral galaxies have thin, delicate disks and appear not to have suffered mergers with large galaxies. A galaxy moving through the gassing cluster of galaxies can be stripped of its own gas and dust and may become an S-naught galaxy. Rare, isolated galaxies tend to be spiral, which suggests that they have not suffered collisions with similar-sized galaxies. At great distance and great look-back time, the largest telescopes reveal that galaxies were smaller, more irregular, and closer together. There were more spiral and fewer elliptical long ago. At the largest distance, astronomers find small irregular clouds of stars that may be objects that fell together to be forming galaxies when the universe was very young. I think it's enough for today. Any questions or propositions? So I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.